Welcome everyone. Welcome to this sixth session of Quantum Computing in a Nutshell, powered by Open Science Labs, Brazil. In the past previous sessions, we have discussed way more topics regarding quantum mechanics as well as quantum physics. In the last session, we had discussed about the QIS Kit software by IBM, which is a open source Python library which is used for building quantum circuits. I gave a small introduction about the quantum library by IBM. In this session, I have built some quantum circuits as well as quantum based analytic tools which can be used for various operations in quantum computing. In this session, we are going to discuss as well as gone through the softwares and frameworks which I have developed for quantum computing. Uh, for newcomers, I am Sri Kalishwarar and postgraduate from India. I'm doing my postgraduate degree in physics from India, and also I am an independent quantum researcher associated with various organizations. Uh, for a brief introduction, the program will be in Python, but don't worry about that. I have some presentations to explain which kind of frameworks we are using right now for the basic understanding. The code itself not only programmed by myself, I also used large language models for programming, but the basic understanding about the quantum infrastructure as well as quantum computing architecture is way too important to understand the concepts of these pipelines. For most, we will begin with the quantum analyzer, which I have built called Music Analyzer. One second, let me screen share it. The entire screen is sharing. Okay. I hope my screen is visible to everyone right now. Okay. Now, here is the thing. I hope the screen is visible. Here, I didn't even use any external library for this processing. Uh, Here, it is one of the most basic methodologies we can use for quantum computers to represent the quantum computers. Here, I am using two music files, both of them in my native language, Tamil. Both of them are both of them are identical Tamil songs. Here in this part, I have done something uh, unique. Like I have two versions of the song. One itself played by the person itself, and also another one which is recorded on a concert. For copyright issues and other protocols, I couldn't able to present the songs here in this live session, but we will look at the code itself. I hope. I have already saved the file inside a folder called Music Analyzer. I have saved both of the MP3 format files, both of the song files. The song name is Ilaya Nila Polihiradu in Tamil. The both of the files are in the same MP3 format, but both of them are same identical songs, but both of them have recorded in two different environments. So let me compare both of the songs using quantum analogy. Uh, I hope you can see my screen here. I have used NumPy, which is an array manipulation tool available in Python. Also, I have used SciPy for signal processing as well as spatial distance measuring. I have imported the cosine component here. Also, I have used SciPy for some other things. I have used Librosa, which is a open source Python library, which can be used to uh, handle music files like MP3, FLAC, MP4A, and other file protocols. What we are doing is we are converting the audio signal into a digital signal using time series manipulation. Also using the Fourier transformation, we are getting a frequency spectrum here, and using the Hankel matrix, which is a matrix representation which is available in quantum physics. We are using the Hankel matrix to represent the state space representation, and we are mapping the qubits in -1, 0, 1 state. Uh, for basic analogy, beforehand, I will run the file here now. One second. Let me maximize my terminal for your better viewing. I will zoom in once again. Okay. I hope this is visible for everybody. I'm using Python 3 music analyzer. Sorry, let's type into it. Again, Python 3 music analyzer.py. I hope the file would run right now. We'll wait for some time for the file to be get executed. Second, I think the processing is going on right now. We will wait for some time. Okay, the process is going on here. It is processing the second audio file right now. I use those errors. It usually happens due to the without the missing description in the thing. We will wait again. Okay, now we have the output here in our screens. Let me explain this once again. Here we are using quantum qubit spin state representation for representing our audio signals here. We are representing those high pitch lines as +1 state, which is mentioned here in a chronic in a Ket notation, which is a high state. We are mentioning those humming sounds in a mid state called 0 state, and also low frequency audio signals. We are using cosine signals here. We are using the negative components in the -1 state. This is the original reference track of the music called Ilaya Nila Purigirathu. Also, we are using the same identical song which is recorded in another environment, and we are finding those quantum mismatchings here. Basically, what we are doing here, like we are comparing both of the information using quantum cryptography. We are comparing both of the states of the music with cryptography, and we are finding that there is a ton of mismatches in the information. This representation is gives the basic understanding for the quantum based uh, information transmission technologies, or maybe quantum cryptography, quantum information sharing protocols, which is explained here. Like, we are basically comparing both of the audio signals. We are representing both of the audio signals as qubit spin states, and we are comparing both of the informations here, right here, and we are finding those mismatches and giving an output. Like, uh, basically we are representing those audio signals in terms of qubits. This is the basic analogy of quantum computers. Like, if you are doing a mathematical calculation inside a quantum computer, this thing can be identical to a quantum superposition and quantum entanglement. Also, this can be used to represent the quantum error. Things like, we can uh, consider these mismatches as also as quantum errors, because we are using both identical sounds, which have some smaller differences. But in reality, even though it is a 5-second precision grid, which is a low precision grid, we are finding potential mismatches here. In the real quantum computers, if we have these kind of mismatches, that will that leads to wave function collapse, or maybe the information lost in quantum computers. This kind of things would really happen inside a quantum computer when there is an external interference in the incoming signal. That could happen potentially in the quantum computers in the modern day. That is why IBM, Pennyland, Microsoft, and other world famous organizations which are dealing with quantum computers are trying to reduce those quantum errors. Here, we are just comparing two audio signals, two audio files, and we are just simulating the quantum error concept here, because we are representing those audio signals, two identical audio signals in um, qubit states, and we are finding potential mismatches in the audio frequency signals in terms of qubits, and we are mimicking this here. For this framework, I didn't even use any QoS kit or any other platforms for this approach. I had just used native Python and SciPy representation for linear calculation, and also I had used uh, matplotlib for this plotting purposes. Um, in this code, you can actually see. One second, let me launch it out. Again, we are setting those Fourier transformation analysis as 2048. We are using integer streams. We are using a 100 millisecond precision here. We are using Hangul matrix, which can be linear algebra, which is a linear algebra function, which can be derived from SciPy. And we are also making qubit states in terms of 1 and -1 states. We are basically converting those algorithms into qubits, and we are plotting those information here. I have mentioned the both of the files here, right here. You can see that. Well, basically, this is my first framework which I have developed in terms of explaining quantum computers as well as quantum cubic states. For the next level, I had developed another thing here. One second. Let me start up from here. I hope my screen is visible to everyone. Here I have built a 13 layer quantum based stenographer. Stenographer means information encoder as well as decoder framework, which is a research level framework which I have built here right now. Let me run this file first. One second. Copy this once again and paste this here. We will wait for a few minutes until the code is get executed inside our Python process, inside our Python IDE. The file got executed right here. Basically, what we are doing here means, one second, let me zoom in. One second, zoom in. Okay. Uh, the information is retrieved here. I think we had lost the graph. We will run this once again. Copy this file, paste it here, run this. Yeah, now we have the figures. Once again, let me. Okay, basically, what we are doing here means uh, the same approach which we have done earlier in the audio signal matching system, or maybe the qubit audio comparison system. Here we have done something far more greater. We are converting the information. Basically, uh, let me draw something in this tablet. Let me say one, or maybe eight is an information, which is a text information. In computer language, we call them as ASCII code or ASCII2 code information, which is a standard protocol which is used to convert the digital signals into text and text into digital signals. Basically, we have converted a text into ASCII code. Then we have converted into a wave, maybe a legendary expansion. Then we used a Markovian transition matrix to represent it as a matrix. Then we used, like, this part is an encoder part. We have encoded a digital written information into a, basically, the written information into a wave information. Then we converted them into this Markovian transition matrix. In this step, we have used the QIS kit, which is the IBM's QIS kit framework. We had built a augmented or a simulated circuit here, and around 8 qubit circuit here. Then those information, then the encoded informations are decoded by the circuit, and we have got the two plattings here. Like, this is the greener one is our initial wave, the final one is our output wave, and this output wave is then converted into ASIC code, and we got our information back. Basically, what we are done here is so fascinating. We have converted the basic information, basic English language information into a wave function. Then we converted it into a Markovian matrix, which is a matrix representation which is used in classical mechanics as well as in quantum mechanics as well as quantum computing. Then we fed the Markovian matrix information to our quantum decoder circuit. The circuit was able to decode the information and retrieve the original information from it. Basically, we are just created a information carrying system, or maybe a quantum stenographer. It is basically getting an information, encoding it, then fed it to a quantum circuit which decodes the information, and we get the original output out of it, which is really a fascinating thing in quantum cryptography, which has a ton of novel information inside of it. Let me reveal the code for this thing. I hope my screen is visible right here. We have run this file Q13 layer. Uh, we are using CSV library for CSV file formatting, because the output information will be exported to our CSV file. Uh, the input information is basically, once again, the input information, input secret message is free SRI. The encoding 3-bit quantum resistor, which has a 8-dimensional property. The output information got retrieved, the original information got retrieved around 99.99%. The information got reconstructed successfully. So we have done a real-time quantum stenographer, or maybe a quantum cryptographic encoder and decoder circuit here. We had used NumPy, Pandas, SciPy special functions, SciPy, SciPy linear algebra functions. Once again, also we had used the Matplotlib for our plotting. We had used QISKit. We had used quantum circuit, transpile. Also, we had used the quantum Fourier transformation. The QFT stands for quantum Fourier transformation. AER simulator, augmented quantum circuit simulator. Also, we had used the state vector and state fidelity functions, which are basically available inside the QAS kit. We have our first layer. We are basically converting our text information into a audio signal, or maybe wave signal. We are using these manipulations here. We are converting them into an array. Then we are creating a 1D, one-dimensional wave equation simulation, maybe an acoustic wave. We are using one-dimensional wave equation here, c into dt by dx the whole square. We are finally created a wave equation, and this part is basically our output part. We are have an automated CSV as well as XLX, I mean Excel sheet output format, output getting protocols here. We had used this, and also here we are using continuous field and quantum resistor state array functions, which these functions are basically derived from this particular NumPy system. We are using Legendre fit equation, Bessel polynomials, and we are calculating the initial amplitude, final amplitude of the signal, and the main pipeline is here for our execution. We are converting the AS to code conversion, wave equation, Legendre polynomial expansion. We are using Legendre polynomial for expanding our waves. for expanding our wave frames here, we are using Bessel function for frequency and phase modulation. And another time we are using Hungel matrix and Markovian transition matrix. We are using two matrix protocols here for our stenography. Initially, we had used only one protocol in terms of Markovian matrix, but here we are using two protocols. Here we are using superposition quantum register initialization work, and afterwards we are going to create a quantum circuit with the help of IBM QIS Also, we got the final output and other protocols here we have used. And also we had used uh, Matplotlib for our visualization purposes. We had visualized the values here, and the output significantly shows that this protocol was able to this 3-qubit circuit was able to successfully uh, transmit or encode and decode the information successfully. We had a 99.99% success rate here, which is a novel technology, which is a novel approach which I had mentioned. These all approaches are entirely uh, initialized by me. I had gone through all the existing protocols which are available, and finally I tried with these. Okay, and we have yet another quantum waste pipeline for you, which I have developed earlier. One second, you may have this in my recent files. Uh, Sorry, yes. It's quantum steno.py. One second, let me open my terminal here. Mm, Quantum steno. One second. We need to follow Python actually. Yeah. Once again, I think we got the plotting. Yes, we got it. Let me explain this once again. This is our image. Let me consider this. This is our pixelated image. We are using 2D quantum Fourier transformation. Initially, in this function, we used one-dimensional quantum Fourier transformation. Here, we are using two-dimensional quantum Fourier transformation. We have transformed this original image into quantum Fourier transformation frequency spectrum, and then we used a decoder protocol to get this information out of it. This is our absolute error map. We had a very less amount of error, around 0.4 percentage error, which is basically a 4 into 9.2 to the power of 10 to the power of minus 1, exponential minus 1, which is a very low error record. But in visible way, you can see there is some pixelated uh, missings in the two images. Basically, we are just converting this image into a quantum Fourier spectrum, and we are retrieving this image again, which is a stego image. Stego image. We got around 17.1 decibel here, and we had a loss, absolute error map, which is basically a 2D information decoder as well as the encoder protocol. Let me reveal the code once again for you. think this would be the perfect code for everybody to see. We had used NumPy, Matplotlib, PIL for image conversion. We also use Quantum QIS kit for our quantum circuit creation and quantum Fourier transformation, state vector, and set fidelity. We use 2D image pre-processing and amplitude normalization protocols here. We had a 2D image. We had generated a 2D image, synthetic real-world featuring image, which is basically some graphical image which can be handled by my computer. In the upcoming sessions, we will going to use real world images, and we will try to recreate that image using quantum Fourier transformation in the upcoming sessions. Initially, we had done this here. Once again, let me explain all the code. We are pre-processing the image, and we are converting those image into qubits architecture using Fourier transformation. Then we are putting this into the basic quantum circuit protocol. And finally, we are getting the output image. Basically, what we are doing, we are transmitting images. We have a 2D image, maybe this or anything else. We are converting this image into, once again, into a signal, and afterwards we are decoding it and retrieving the information, which is also a fascinating thing in terms of quantum cryptography as well as quantum information, which is also a fascinating thing in the quantum computer states. And here is our final code. I think we have our final code. Again, okay, let me run this. I hope this would run. Is the RMT? Why it is not running? Okay, we will test this once again. Like for this, in this session, we have discussed about three quantum circuit protocols. First one doesn't even use those QIS kit software. We are just representing the qubit states using two identical audio signals and trying to find the information matching, which comes under binary or maybe a qubit information sharing. On the next step, we are used a protocol to transfer and text information, ASCII to code information, and we had successfully retrieved the information 99.99%. On the third step, we tried to recreate a 2D spectrum, and around 99.5 percentage accuracy, we have recreated the information successfully. And this is the thing we have done for here. In the upcoming weeks, we will going to do way more complicated quantum circuits. Basically, most of the people may think like maybe you are watching this live stream or maybe you are watching a recorded session of this. Most of the people think that the quantum circuits are only belongs to the people who are working in IBM or maybe Pennyland or maybe the developers from QIS Kit or maybe working in a fancy laboratory. Basically, I am just a student using a very old laptop in my hand, but I can also build a quantum circuit with the basic hardware I can also build a simulated quantum circuit with the very basic low level hardware. And also, I can create new techniques for quantum information sharing as well as quantum cryptography. These researchers, these programs, these circuits are going to be published as research papers in the future, and I will also share this information to others. Basically, this day would be one of my disappointing days because none of the people were present in the final uh, discussion part of this event. Anyway, I don't want to worry about it exactly. Uh, for others who are watching this video, I think there is a network interruption there. Once again, let me screen share. Try screen once again. Okay, for those who people who are watching this video, I hope everybody have the access to the basic computer hardware in your environment. You can also create a quantum circuit without having that much of knowledge in terms of real cryogenic, cryo-based quantum chips. We can manipulate those quantum states just by using the hardware which we are currently having. And we can also learn quantum information, quantum cryptography, quantum encoding and decoding processes without uh, any help of other softwares which are available. Most people thinks that you can only learn quantum computing when you are working with IBM or any other fancy office, or maybe doing your PhD in MIT, USA, or maybe any other world-class universities all across the world. I just want to mention I'm a person who is doing this as a community service. I am doing these live sessions without any expectation uh, for the society. Uh, Within my resources, I can do this. I hope most of the people can do this way more from this. You can buy this kind of mathematical books. I'm using Chrysek's Advanced Engineering Mathematics, published by Verley. Also, I am using Nauruddin Zerli Quantum Mechanics book for understanding those basic quantum concepts. Also, I'm using those limited resources to understand the basic quantum concept. I don't have any fancy subscription for those AI models. I'm also using those free AI models to build these kind of basic circuits. And some other professors may be watching this video from any part of the world. If you are interested to get connect with me, uh, you can visit my website. You can get the full information just by go to opensciencelabs.org. You can got into their website. When we go into the community partners section, you will find quantum computing in an Excel by Sri Kalishwara. You can go on into more details. You will find my personal blog page, Sri Kalishwara's Home. Here you can find my Discord channel link. You can join on my Discord channel. You can contact me from here also. Also, if you want to appreciate my initiatives, uh, you can leave a comment in this video, which I will watch for sure. In the next session, we will discuss way more about quantum computing, deep about quantum computing. I hope that session will be way too useful for you. For a summary, we have discussed about qubit-based audio quantum frequency and qubit spin state audio comparison protocols. We had discussed about the wave propagation and 1D technology, which we maybe the one-dimensional quantum Fourier transformation and retrieving a AC2 information or maybe text information. We also discussed about the stego image processing system protocol in terms of quantum computing. We have successfully retrieved a image from out of it. Also, currently, I am also developing open source quantum software for everybody. I hope I will publish the software maybe in the upcoming weeks. You can check it out. You will find all these things inside of it. That would be a super Linux distribution. I'm also planning to build a Linux distribution, Linux desktop distribution for quantum computing. That also will have a ton of quantum computing stuff onto it. I hope this session finds you very well. Meet you in the next session. Uh, Once again, I forgot to mention this thing. We had used Legendre as well as Bessel model shaping for this. We had also used Hilbert space amplitude encoding techniques in our session. Also, we had used 2D quantum register architectures. Particularly here, we had used 2D quantum architectures. We had used quantum Fourier transformation, 2D quantum Fourier transformation. We used the 2D spatial frequency momentum spectrum, which is represented here. It is a spectrum, but you can't uh, differentiate those information with your naked eye. We will discuss it later. We also discussed about space uh, ste- steganography injection. This is also a quantum-based protocol. We also used bond rule stealth zero loss technique. We are, we actually minimize those uh, error. In the theoretical part, we would get very low error, but here we got around a maximum of 0.5% error here in the real world. And this is the thing we have done here uh, for today's session. I hope this session is entirely based on quantum computing. In the upcoming sessions, we will discuss way more on this topic. If you have any doubts, you can reach me on our Discord channel, as well as YouTube comment box, as well as the website of Open Science Labs, as well as on my personal blog page. We will meet in the next video, next session, uh, conducted with the help of Open Science Labs. Thank you. Have a nice day.